So thank you. Thanks again for the kind introduction. And whether anybody says anything complimentary about my knowledge of Spectrum or the company's involvement in Spectrum, it's always followed by a question about Spectrum, which I don't know the answer to, and none of my colleagues know the answer to either, because it's such a wide field and an area that requires many people in order to have sufficient knowledge of all the aspects of it. So I'm very pleased to be chairing this discussion about 5G and environmental sensing, because environmental sensing is an area that doesn't get as much attention as many others, particularly the mobile sphere. And as one of the passive services, the environmental sensing via satellite is listening to signals, not transmitting them. And it's vital work, but it's not something where ordinary citizens feel a direct economic or technological effect. If regulators get spectrum allocation wrong in another field, we might notice our Wi-Fi or our mobile or our hearing aids doesn't work properly. But with environmental sensing, you feel the effects at one remove. The weather forecasts might get worse. Our understanding of global warming might not be as good as it should be. These are all serious things and do have a profound negative effect, but one that we feel indirectly rather than directly. So obviously protecting environmental sensing is a very important issue. On the other hand, to improve mobile services, each generation they've gone higher and higher up the frequency range, meaning that 5G and soon to come 6G are using millimeter wave bands, which are very important for environmental sensing. So how can we get the economic and technological benefits of 5G and 6G without compromising the equally important work in environmental sensing? That's hopefully the question we will try to answer today. And luckily we have two experts in this field from environmental sensing, Professor Gasiewski from the University of Colorado, and from the world of 5G and 6G, Professor Thomas Marzetta from NYU, also the director of NYU Wireless. So I'd like them to make a brief introduction to their field, and then we then look forward to your questions. And if we could start with you, Al.
Thank you, Martin. And I want to thank the entire Spectrum X organizing team for putting this on. This is a great opportunity for dialogue. I want to point out that we live in a rather interesting era in many ways, but in one in particular. We humans have the ability to change the destiny of the planet, the destiny of species all over the planet, the destiny of biota. And we can do it collectively because we have so much authority over the use of carbon. This has a huge impact on the radiative equilibrium in our atmosphere. We also live in a rather interesting time when we have really, after roughly the late 1950s, the ability for the first time to see the planet from space. This is in many ways a bit coincidental that at the same time we have the ability to change the planet's destiny, we have the ability to see it from space. Now, we evolved as creatures seeing red, green, and blue because our sun is basically a white star for the most part. And that really was considerably helpful in our evolution. But if we were to be a species who evolved to take care of the planet, to understand all of its various interacting systems, we wouldn't be seeing the planet in red, green, and blue. We would be seeing it in microwave radiation, because it is now abundantly clear that seeing the planet with microwave eyes, so to speak, with microwave radiation, is the best way to understand it and to predict it. And by predicting it, I don't just mean predicting the changes that we are imparting to the planet through climate change. I mean also predicting the weather that is so damaging and has been damaging ever since humans started setting up their civilizations near coastlines, etc. Now, why do these microwaves play such an important role? And the answer has to do with the penetration of clouds that's possible using microwaves, because with microwave eyes, we can see through clouds essentially. And as this chart shows, down at the low portion of the microwave spectrum, down around anywhere between 2 to a couple of hundred gigahertz in frequency, there are these rather interesting absorption resonances in the atmosphere. These are of quantum mechanical origin, and they're resonances caused by oxygen and water vapor. There are also other gases that cause resonances, but these are really important. When we look at the Earth near these resonances and also in between the valleys between them, we have the ability of sensing a host of environmental variables that are critical to understanding the planet and to forecasting weather and climate. And so it's these variables that we are now measuring through satellite radiometers that we have orbiting the planet that will only become more critical for industry as well as for, again, just the very future of the trajectory of our planet and its habitability. Let me go to the next slide, if I can, please. This next slide describes the challenge that we face. We'd love to use these frequencies and build our microwave eyes to observe the Earth from space. But unfortunately, we are being interfered with to a greater and greater extent by transmitters that are built for communications. Communications, arguably for extremely important purposes, but nonetheless, they also are utilizing the same frequencies and confounding the very signatures, the very variables, the very features we want to see on our planet. And you can say, well, can these two services coexist to some extent? Well, the answer is, as long as one is quiet enough so the other can do its job, the answer is yes. And so there is a density of interferers that comes out of this. Now, I won't go into too much detail in the math unless we want to a little bit later on during questions, but you can only have so many devices transmitting at the frequencies that we need to observe over a given area before our eyes, so to speak, that we are implementing on these satellites become confounded. They can't see anymore. This depends a lot on the transmitted power, on the opacity of the atmosphere, on things like the bandwidth of the channels that we're using, the wavelength, etc. But I illustrate in this little cartoon the picture of interest over here. And that is our satellites trying to look down at the Earth with a spot with its antenna. And in this particular cartoon, there are a lot of automobiles using collision avoidance radar that are scattering signals back up into that satellite's antenna. This is the kind of scenario that we're trying to avoid. Now, this happened to be from 2004 when we were working with the problem of auto collision radar avoidance. But the same problem is beginning now in 5G communications as we start using the higher parts of the spectrum. I'm going to go quickly through two more slides and show you the effects of this interference. So here are images of the US taken with one of the earlier satellites that observed the microwave emission from the Earth, the so-called Simmer satellite. This is around 6 gigahertz. And you can see back in 1979, it was observing effects caused by surface soil moisture, vegetation, number of environmental variables. And it was observing them in a pristine radio environment, very few transmitters operating at those frequencies. As we fast forward to 2004 now in the lower right, we see effectively the same frequency band, little different, not much. And we see a number of places where there are hotspots. Those hotspots are the result of transmitters that are producing radiation that confound this particular satellite sensor. This is an example of the kind of problem we're trying to resolve. Those hotspots make the data in those places unusable. And if those hotspots aren't even known, if they're just a little bit warmer than the background, they can actually throw off a weather forecast quite significantly. Let's just go to one last slide here. I want to point out that a lot of this work is embodied in a document that we produced about 10 years ago now. It probably isn't due for an update at some point, but a lot of things haven't changed. And this is a document called Spectrum Management for Science in the 21st Century. And it's the result of an NRC committee study that was commissioned to study scientific uses of the spectrum using these passive techniques and the threats to those uses of the spectrum. And it looks like that the text down in the lower left-hand corner of the page has been translated by our AI friends here into something unintelligible. But that text basically states that passive spectrum without emissions is the equivalent to parkland that is something that should be preserved to some reasonable extent for all public purposes, inclusive of science and inclusive of weather forecasting. And with that, I will end and be happy to entertain questions as we go along. Thank you, Martin.
Thank you very much, Al. For people here who know less about the subject than some others on the call, could you take us through the uses that environmental sensing is put to? What I'm sure you can talk at great length about this, but give us a flavor of it if you wouldn't mind.
Yeah, so the passive environmental sensing techniques can measure a number of variables that are just critical to being able to predict the atmosphere. One of them is moisture, humidity. Humidity is the working fluid of the atmosphere. Another is temperature. It tells us how much humidity the atmosphere can actually hold. Another are clouds, which tell us a lot about the radiation that flows through the atmosphere or otherwise doesn't. Clouds, of course, reflect radiation. Another is the roughness of the ocean, which has to do with the winds on the ocean, and winds have everything to do with the transport of energy and mass. Additional variables include moisture in the soil. Our soil is like a giant sponge across all of our continents that absorbs moisture and releases it, and has a great impact on weather, has a great impact on the production of food as well. And so these are just a few of the variables that can be observed through these passive techniques. And again, they're important for large-scale modeling and prediction of the environment.
And this would be used through weather forecasting, would be of use to farming, other things as well I haven't mentioned?
That's correct. The insurance industry. The insurance industry is greatly interested in being able to, of course, cover people's losses in the event of weather. And this is an industry that smooths out the entire global economy. When that insurance industry has no ability to predict, then it can't offer insurance for a number of sectors. And as a result of that, our global economy is affected. It's no longer as efficient as it could be.
And global warming, this has a part to play in measuring global warming, I would imagine, does it?
Well, of course, those of us who have studied the radiation effects of CO2 in the atmosphere don't need to be told that CO2 traps radiation and warms up the planet. And we're beginning to see that in a very visceral effect through many, many sources of data. But we'd still like to better understand the mechanisms by how that radiation trapping occurs and how to more accurately tune these models so that we can predict what's going to be happening in the future. Right now, the models predict anywhere from perhaps 1.5 degrees to up to 3.5 degrees C of warming. Those are radically different scenarios. And much of that variability in what will happen is due to the fact that these are complex models that still need to have portions of them tweaked and tuned through scientific understanding. And the only way we can get that scientific understanding is through Earth observations of these sorts.
Well, thank you. No, that's an excellent explanation. If we could move on to Professor Tom Marzetta, who will give us a perspective from the opposite side, from the mobile field, I think.
Yes, Tiffany, if we could see the slides, please. First of all, I'd like to thank the organizers for inviting me to have this opportunity. It's not often that I get to sit down and discuss and debate things with a genuine scientist, Gasiewski, but it's a real privilege. And I was quite intrigued by that slide showing how 40 years could have such an effect on, say, the use of 6 gigahertz spectrum. All right. When as school children 50, 60 years ago, some of us at least go back that far, we were taught that the 3 basic necessities of life were food, shelter, and clothing. But to those 2, I think we can now add electrical power and ubiquitous telecommunications. And both of these are only going to grow. And it's a fact of life that spectrum is a precious resource. And so it's needed for things like environmental sensing. It's also needed for applications which are exceedingly important to human beings. So next slide, please. So those of us who want to do research on how to resolve possible conflicts between scientific applications, environmental sensing, and those who want to put this spectrum to work directly on the behalf of humans have to have certain premises in mind. And this slide illustrates what I believe are some common premises, which obviously I don't fully agree with. So the first premise is that all of the action in the future of wireless 5G and 6G is going to take place primarily in millimeter wave and higher bands. A second premise is that massive MIMO, and I'll explain a little more about that, is being fully realized right now in 5G. A third premise is that wireless systems are somehow operating already close to limits imposed by nature. So I don't think any of these 3 is necessarily true. Let's go to the next slide, please. So the lure of going from, say, 3 to 6 gigahertz to 30 to 60 or 300 to 600 is each decade in carrier frequency that we jump. Guess what? 10 times as much spectrum opens. And so the natural thing is to assume that we can harness this higher frequency spectrum as efficiently as we can lower frequency. So 10 times as much spectrum in most people's minds implies automatically 10 times the available throughput per unit area. This isn't necessarily so. If you want to make this, investigate this, you have to look at what is the most spectrally efficient wireless technology yet devised. This is massive MIMO, and it's to some extent, but not fully being realized in the mid-band sub 6 gigahertz. Well, there is a pessimistic analysis one can do back of the envelope that my friend Erik Larsson from Linköping University in Sweden has made, which basically pessimistically concludes that spectral efficiency, bits per hertz, that you obtain from spectrum is inversely proportional to the carrier frequency. So if this is true, then going from 3 to 6 gigahertz up to 30 to 60 is only going to double our throughput. And that if we go up to 300 to 600, the combined move to millimeter wave and terahertz is only going to triple what we can do in 3 to 6. Okay. This is highly debatable, but I don't think it's I don't think it's been demonstrated conclusively one way or another. And the marketplace has spoken already. So a year ago, there was an auction of 3 gigahertz of spectrum in the 30 to 47 gigahertz band. That represents close to 10% of all of the bandwidth available from 0 to 40 gigahertz. $7 billion, $2 per hertz. Just a couple months ago, FCC auctioned 280 megahertz of prime midband spectrum, $81 billion, $290 per hertz. So roughly speaking, the marketplace seems to say the value of spectrum is proportional to the inverse of the square of the carrier frequency, even worse than what Professor Larsson predicted. Next slide, please. Massive MIMO, how does it work? The whole idea is that instead of what a 4G base station does, which is spew power out indiscriminately over these 120-degree sectors, instead Massive MIMO sends power where it's needed. So cleverly, it sets up independent data streams, all in the same time frequency resources to a multiplicity of users. This means that you're reusing the spectrum again and again and again by all of the users at once. And this accounts for its spectral efficiency. It's also a inherently green technology in that it can permit reduced radiative emissions. Now, it's not being used very well within 5G. A couple of reasons for this. 5G was designed as a back-compatible new generation of wireless. Yes, if you want to take advantage of the new millimeter wave frequencies, you got to get a new handset, but nothing else has been affected by it. This is for the first time we've ever had such a back-compatible new generation. It almost doesn't constitute a new generation. And Massive MIMO suffers greatly because in the form in which it's used in the United States, frequency division, duplex, and even with TDD, they're still using this awful grid of beams method. I estimate you're losing at least 90% of its potential spectral efficiency. And among other things, of course, you have typically many more service antennas at the base station compared with active users. These extra degrees of freedom can be used, guess what, for interference mitigation. Next slide. Next and final slide. The final thing is people somehow think that we're operating close to limits imposed by nature, that even if you got Massive MIMO up and running as it should be in the mid bands, that there's nothing more to do there. I don't think this is so. Shelkonoff in 1943 showed that there's essentially almost no limit to what you theoretically can do with antennas, transmit antennas in a given small volume of space. I'll stop here. Thank you.
So committing the cardinal sin of webinars there for having myself on mute, but now putting myself back off mute. I wanted to ask you how what you were saying there, the myths that you were pointing out, how do they relate to environmental sensing? Does that mean that it's easier for the two to be compatible or not?
Well, one thing it means is that if these premises are in fact myths to a great extent, and if these are the premises that people are doing research on reconciling 5 and 6G operation with environmental sensing, then it says that at least some of this research is off in the wrong direction.
What do you think they should be researching?
Well, it's one of the things is my personal opinion is that even though millimeter and terahertz are potentially incredibly valuable just alone for communications purposes, that we need to do much more research to make it happen, that we shouldn't regard this as a done deal. And in fact, that perhaps a disproportionate amount of attention in wireless research is going towards these higher frequencies and could better be directed at more fundamental research aimed at the mid-band.
So if there was more of a focus on mid-band frequencies, less of a problem for the environmental sensing, which tends to use these higher bands.
The other thing is some of these problems are matters of, call it political will, if you wish. So there is great concern, of course, about interference in the 25 megahertz or gigahertz bands, or approximately, with these new NOAA passive satellites that are trying to, as Al said, measure critical physical parameters. Well, how do you deal with that? I mean, there is, I believe, a couple hundred megahertz of separation, but there still is the possibility of out-of-band emissions. So, maybe it's easier said than done, but why not more strict emissions regulations on the part of FCC? They have the power to do that. They could obtain, I'm sure, the money to set up monitoring stations to really crack down on anybody who exceeds whatever the agreed upon out-of-band emissions are. That's not a high-tech solution. I don't know what exciting new research. There is some, obviously, in terms of low-cost monitoring of this sort. I believe some of this is going on by my friend Bert Hochwald at Notre Dame. But yeah, there are things that you can do which do take political willpower and are not going to be solved just by clever research.
So more of a question of preventing interference, more money, more resources, more monitoring to ensure that devices don't go over their prescribed power limits, and indeed stricter power limits. That seems to be what you're saying there.
Those are things that can be done. Now, as this, again, I personally think that the mid-band is always going to be the most valuable spectrum, and considering how much the AT&Ts and Verizons are willing to pay for this spectrum, $290 per hertz, there ought to be more research money available for making better use of this incredibly valuable spectrum.
Thank you. We're getting some questions, so thank you very much for the questions from Petri and Phil. We'll come to those in a moment. I just wanted to go back to Al and ask him if he was felt any more reassured by what Tom had just said, and then we'll move on to further questions after that. Al, if we could move over to you.
Thank you. Yes, actually, I am somewhat reassured to hear that there's not as much economic value in the millimeter wave versus the, let's say, below 10 gigahertz portion of the spectrum is quite encouraging, because as we all know, economics do drive a lot of what we do politically. And if that's something that really holds, then it would be great if, from the political standpoint, we could be lumping the usage of the millimeter wave spectrum for telecommunications into bands that are reasonably far separated from those bands that we use for passive earth sensing. So I've got a great deal of what you'd call encouragement that we'll be able to do that just from the economic issues alone. However, this is the big if. The reason that the millimeter wave spectrum may not be valued so much today is because of technological shortcomings. And these technological shortcomings are rapidly being themselves overcome through research into lower cost methods of producing transmitters and receivers, higher power devices, antennas with more adaptability, for example. And so if you look back at the same, what you might want to call value of even the, let's say, X-band portion of the spectrum, about maybe 20, 30 years ago, you'd find a similar disparity. Of course, all the TV stations were using 100 megahertz, a couple hundred megahertz, et cetera. That was where all the action was. Nobody even thought about X-band or C-band as being valuable parts of the spectrum. That's changed considerably now. So while I'm encouraged by Professor Marzetta's comments in that regard, I'm not under the belief necessarily that that economic argument alone will create the political will to ensure that we remain viable for passive Earth sensing in the millimeter wave portion of the spectrum. And then this doesn't even address the needs that we do have below 10 gigahertz as well, which are somewhat separate, and they're confounded by the extremely high value of that spectrum.
Thank you. Well, if we could move on to some questions. So the first question was from Petri Mahonen. He said that we've done some modeling of 5G interference against remote sensing satellites at 28 gigahertz, which seems to be true. But for Al, apart from generating bias through constant interference, how serious do you see the interference level that can change dynamically in the space-time axis? So thus, do we need to worry about both level and variance, says Petri?
Level and variance are important. Population density is important as well. And unfortunately, a lot of our weather forecast needs really are in coastal areas. And the coastal areas are where we have a lot of population density as well. Now, if we have truly a threshold that is scientifically derived to ensure that we have no interference at the level of what you might want to call criticality in our passive sensors, then I think that there's no reason we can't have these active devices operating in these vicinities. However, this is also something that is politically dependent, because as we go from one administration to the other, at least in the US, we tend to have different levels of, I'll say, critical respect for the mathematics and the science that underlie these arguments. And so we want to make sure that these thresholds for interference are able to be maintained across administrations, because it's in both, you might want to say, political parties, if you will, interest to ensure that we've got a livable planet and we've got weather forecasts that hold. Yet it's not necessarily the case that those kinds of threshold arguments carry across from one FCC to another.
Well, on a similar subject, we had another question for you from Phil Erickson, which was, how much impact does the coherence of the interferer make for the science case, e.g. bright coherent radiators versus lots of incoherent radiators?
In other words, how much more serious is coherent versus incoherent radiation?
Yes, I think so.
Essence of the question, yeah. Well, the answer is coherent can be roughly a factor of a couple worse or so, give or take, a factor of 2 roughly. It's really the collective superposition of all of these radiating powers, collective amount of them, that cause the effects that we can't get around. And this is more of a problem of the fact that many of these emitters that we're now considering licensing are unregulated in the number of them sold. In fact, it's to the company's interest that so many of them are sold that their economic bottom line is floated, et cetera. There's no limit on them. And so as a result of that, this densities of interferers equation that I mentioned is a very hard one to utilize, just because we can't control the number of interferers that are produced. Now, let's say for the sake of argument that in a city the size of, let's say, Chicago, only 1 million cell phones would be issued and allowed. Of course, you know how long people would stand for that. That would not be in any way politically acceptable. And the same thing goes for all of these now 5G devices. There's going to be no what you'd call a political limitation on the number of them that are permitted. And so we have to assume a worst case in some regard. And with electronics, it's really hard to assume a worst case about how many of a given unit will be issued. I used to think that once everybody had their own cell phone, that was it. We would have no more interference, at least from a standpoint of the amount of aggregate emissions. I'm no longer convinced of that, though, because of IoT devices and other sorts of devices that are now cropping up that don't even need a human operator. And so we no longer have those kinds of nominal and natural restrictions on the number densities of emitters that are popping up in these bands. But to get back to the question on coherent versus incoherent, it's really the summation of all of them, and the coherence is less of an issue.
Actually, coherence creates an better opportunity to remove it. If something is completely random, there isn't a great deal I can do with respect to signal processing. A coherent interference, on the other hand, you can do much more. Now, part of the difficulty is, I believe, the bit rate, for instance, of this new NOAA satellite, the passive microwave radiometer, or whatever it's called, is very, very low. So probably in that generation of satellites, I would guess they're doing a lot of pre-processing up in the satellite and sending minimal amounts of raw data back towards the ground. So one answer, again, which is partly political, is a new generation of much more sophisticated satellites with much higher data rates that would permit more sophisticated signal processing to remove interference. Another point I simply wanted to make is that science does have to adapt to the environment. So when I was a grad student at MIT, I lived not very far from the old Harvard Observatory, which in the mid-19th century was a premier research instrument. But of course, light pollution in the Boston area spoiled that at some point. Well, astronomers didn't give up on astronomy and telescopes. They moved their telescopes to better locations at cost. Yes, at cost, but that's the way it always is.
Thank you. Well, we have another question from David Lubar, who says that although everything Al said is correct, I do ask, do people really understand how vastly different radiometer measurements are from millimeter wave or terahertz communications use? The entire atmosphere volume must be characterized using the absorption lines shown to achieve a weather forecast. The Euro or GFS models that everyone depends on to use this data, measuring the floor fluctuations in tenths or a few Kelvin by passive sensing, can be easily contained by out-of-band emissions from the communication signals. Those out-of-band emissions really key to the efficient use of the communications band? Communication engineers may not be overtly concerned about emissions at or below the noise floor. What's your view on that, Tom?
Could you repeat the question, please, Martin?
Yeah,
or rephrase it, perhaps.
Yeah, I think essentially saying, are the out-of-band emissions really necessary in order to use these bands efficiently? Can the out of bands emissions be contained more effectively than they are now?
In principle, you slap on better and better filters at the base station. And whatever it is the manufacturers are doing, the Nokias, Ericssons, and so on, they're doing it to abide by whatever their regulations are on emissions. I'm sure they don't throw extra filters on to buy another 10 or 20 dB if they feel they don't have to in order to abide by the regulations. So again, stronger regulations in principle can always be implemented, formulated.
Do you accept the argument that these filters make the base stations more and more expensive, the communication process more expensive and therefore uneconomic, perhaps?
They certainly will add to expense. This is a very wealthy industry. There's a lot of slack in it. As I pointed out, AT&T and Verizon and company were able to come up with $80 billion in cash, which they had to 3 days after the auction to make their bids good. There's money there.
Yeah. So we had a question from Scott Palo. A lot of discussions about the 24 gigahertz band, but he'd heard that the 50 gigahertz band could be impacted as well and could be even more important. From an earth science perspective, what measurements are made at 50 gigahertz compared to 24 gigahertz? That sounds like a question for Al.
Yes, and that's a fairly straightforward question because there is a water vapor absorption resonance at 23 gigahertz that we observe for measuring water vapor. And there is an oxygen absorption band around 50 to 58 gigahertz that we use to measure temperature. Water vapor is highly variable, but oxygen is not variable. And so when we measure around the oxygen spectrum, we actually get temperature out of that. And are the 50 to 58 gigahertz bands subject to out of band interference? Yes, we're particularly concerned about second harmonic output from 5G transmitters that are being implemented in the range from roughly 24, 25 gigahertz up through 31 gigahertz. The second harmonic emissions would fall directly into this 50 to 58 gigahertz sensing band that's so critical for temperature.
There's another question here from Dennis Robertson, which said, why has it been nearly 10 years since the last NRC study, given the Green New Deal and all the rest of the high-profile concerns that have been issued? It seems an update of the document is critical, he asks. You think correct?
I could only agree. NASA updates its science plans every 10 years through its decadal surveys, and it's been about 10 years. The science behind spectrum use doesn't change all that quickly, though, frankly. So is it due for an update? Probably in the next 5 years or so.
A question from Nick Laneman. What spectrum should we give high data rate satellites for their downlink?
That was just a little tongue-in-cheek, given the context of Spectrum X and.
Okay.
Martin, can I answer that question of what spectrum we should use for satellite downlinks?
Sure.
The answer is optical or infrared. The bandwidths will be so much greater. The burst capabilities for sending data down will be far greater than what we're going to be able to get out of the microwave, in particular the low microwave spectrum that's under such demand. The downside will be transmission through clouds, which simply doesn't happen in the optical and the infrared portion of the spectrum. However, depending upon the application, if satellites, for example, that are using optical and infrared for downlinks are also networked in space, then there will likely always be some place on the planet where there will be cloud-free atmosphere for those downlinks. So I'm very optimistic that far higher throughputs to satellites will be able to be obtained ultimately as we develop optical and infrared downlinks.
Hmm. There was an interesting question here as well about, given that the bulk of the planet, this is again from Dennis Robertson, given that the bulk of the planet is covered by water and the density of emissions over the oceans is near zero, does that offer some possibilities? Dennis is asking.
Well, it certainly leaves the oceans a little more pristine for observation, although there are, of course, ships, and there's more and more ship traffic all the time, more and more IoT devices on ships as well. So that's not the panacea you might think it to be. Secondarily is that satellite downlinks for communication purposes reflect very well off the ocean's surface back up into our satellites. And so we see this interference already around 18 gigahertz, reflections from geostationary broadcast satellites back up into the Earth remote sensing satellites. And then finally, there's a critical region around every continental shoreline out to at least 500 kilometers where significant coastal weather occurs. And as your satellites pass over those regions near those coastlines, if they're confounded right at the coastlines, then that can impact the prediction of that weather in those coastal areas. Nor'easters, for example, hurricanes near landfall are very damaging events that really could be predicted better even now.
There's an interesting point from Scott Palo here, which I think does bring out some of the economic issues behind this whole debate, and he points out that we strive for more capable space instruments, but NAOA satellites take a decade or more to develop at a cost of $1 billion for the satellite plus launch. Additionally, moving more data from the satellite requires more spectrum for downlink in the already crowded X-band. Does that issue point to the huge economic problems of trying to move spectrum to somewhere else, or trying to sort of change existing uses once they've been put in train?
It certainly is a consideration. I mean, I know nothing about satellites and satellite design, but I gather they're all 10 years out of date practically by the time they start to fly. This is just and I think Al's optical solution or optical relaying solution among satellites is a great idea. Yes, it is a question of economics and cost benefit analysis. You have to weigh these things. Nothing you do has 100% benefits everywhere. Let's look at it. 200 years ago, you could probably see the Milky Way from downtown New York City. But of course, all the light pollution, emissions from automobiles, power plants, and so on have, of course, made that practically, I suppose it must happen occasionally, but not very seldom. What are we going to do? Close New York City down so we can see the Milky Way again? It's a trade-off. There's always a trade-off in technology.
Do you think that, looking at this not from as a scientist or as someone who develops these things, but I suppose as someone who follows the ins and outs of policy and the international negotiation, it seems to me that it takes so long to agree on bands that you would use for 5G, and you need to do that in order to get the economies of scale, in order to be able to produce the equipment at a feasible price that people can buy. Is it really possible to be, once you've sort of set that in motion, is it really possible to be moving it to other bands, like having sort of retrospectively discovered that there's more of an impact on it, environmental sensing, than we imagined. It seems to me that we're sort of stuck with what we've got as 5G bands. Do you think that's the case?
Well, I could speak to the life cycle of weather satellite development, and generally speaking, from concept phase to launch to decommissioning, that can be a 30-year period. We do have weather satellites, for example, the US Navy's WindSat satellite that measures ocean wind direction that was launched in 2000, I think it was 2003. It's been so long ago, I'm almost forgetting, but it's still functioning. And that satellite was conceived of in terms of its design in the early 90s. So these lifetimes are fairly long. Now they are getting shorter because we're figuring out ways of more rapidly instilling new technology. But the bands that we use for the observation, those really can't change too much. If anything, there is a need to even go further out in frequency from these lines, although, again, that's being done at risk that there will be interference.
We had another question from Petri, which was a question to Tom. The point was, one of the problems is that 3GPP and industry is mostly in incremental mode in their development of technologies like 5G. So how could we change that trajectory to think more out of the box, particularly in mid-bands? Or more specifically, what could this Spectrum X community do to enable that? That's a question to Tom.
That's a great question. So again, there's a contrary point of view. There's a conventional point of view. It seems most people regard us as living in an era of lightning-like technological change. But these new generations of wireless occur at only 10-year intervals. 10 years seems like an awful long time for a new technology. My favorite example of rapid technological development goes back to Thomas Edison. He started to develop his electric lighting system in 1879, and 5 years later opened the Pearl Street station serving a square mile of lower Manhattan. That's technological progress. So what's going on here? We, among all the people here, I think I hope we have an economist or two. But it seems to me that much of this perhaps goes to the depreciation time for wireless base station equipment, which I gather is on the order of 10 years. So in other words, the Verizons, AT&Ts, I suspect are reluctant to replace their old equipment with new equipment if they can still get some tax advantages out of the old equipment. So why not permit more rapid depreciation and encourage quicker turnover of the equipment? But I'm venturing on thin ice here.
Yes, that it's interesting, your reflection about the sort of the politics behind this. What do you think could be done at a regulatory level, which would help the environmental sensing? Do you think this is a problem that could be resolved just through environmental issues? Just through regulatory issues, that it's okay to use the bands that have been sort of assigned for 5G, that they can be managed in a way that would prevent interference to environmental sensing? Do you think that's possible?
I don't know, but my thought is that we should really try to avoid absolute statements on this. To say that nothing should be permitted commercially at, say, 25 gigahertz irrespective of what measures are taken by industry to push down the emissions, is not a responsible sort of statement. Instead, it should be said, these are the maximum emissions that should be available. Now, maybe these are 2 orders of magnitude more drastic than what FCC has now, but at least it's a tenable position, and in turn, engineers can say, yeah, we can do this. This is what it will cost. This is what it will cost in wasted power. Again, nothing that you do in technology is positive on all fronts. It's always a matter of balancing the consequences. Another thing with respect to the satellites, yes. If all of these new forms of rocketry, reusable rockets and so on, which again, I know nothing about rocketry, really pan out as their proponents promise, then maybe you don't have to put these dinosaur satellites in orbit. Maybe you can plan on putting much smarter satellites up more frequently, and maybe economical to do so.
Al, you were going to make a point.
Oh, I just want to echo Professor Marzetta's comment that regulation of emissions is the first level of protection for the passive services. And regulations that are based upon statistically proven scientific interference thresholds are really critical in this regard, because it's only these kind of regulations that people can all agree on, that are written out in black and white and understood for their scientific basis. But there is one more incentive-based means that I think has some potential in the future. And this has to do with the fact that the active communication services, they also want interference-free channels. They don't want somebody else transmitting at their same 5G band in their direction and interfering with them. And so in some sense, there's a little bit of a commonality here. There's a Venn diagram where we all have the same goals, and then having interference-free channels when we need them. If there was a way whereby there was called a broker that was able to dish out go or no-go signals on transmissions to users who politely and humbly requested, let's say, a millisecond of access at a given 5G band, and they were willing to listen to that broker as an authority, then we might have a system whereby there's an incentive developed to work within the system to better your own throughput. I liken it to the following scenario. Imagine getting across one of those piazzas in Europe that we've all walked across or driven across, where all the cars are going in different directions, trying to get across there. If it weren't for typically a traffic cop standing in the middle saying, you can go, you can go, you can go, you can't go, then there'd be a lot more bumper collisions. Nobody wants that. So if there's a broker who's respected in some sense, not necessarily anybody with legal authority, but respected for providing go, no go bits of information on transmission, it's possible that you might have both the passive and the active services buying in to the use of that broker to provide what you'd call intelligent decisions on whether to transmit or not. So I hold out some hope that there are other means other than pure regulation, in other words.
Tom, is that a feasible technical solution from your point of view?
Well, the traffic cop analogy is this idea of you grab spectrum depending on whether anybody's using it or not, and you hope that somehow you get maximum use of the spectrum and minimum interference. That's an area of wireless I've never worked in. There are others here who could perhaps comment on where that research stands right now and how promising it looks.
There is speaking, as you probably gathered, from London and not the States, unlike most people on the call, I think. looking at it from a sort of a perspective of Europe, there did seem to be rather different approaches when we went to discuss the environmental sensing in particularly the 26 gigahertz band. At WRC 19, the States was happier to have lower interference thresholds, and Europe was arguing for higher interference thresholds. Do you think that reflects a different perspective on either sides of the pond, or do you think it's been sort of evened out now that the compromise has been reached? And does it matter that you would have a different attitude on the different sides of the Atlantic?
Well, historically, we've been in a tremendous agreement over the years about these threshold levels that are damaging to Earth observations. That is the US and the member countries of the ITU in Europe. And this has been, for the most part, again, due to a great deal of cooperation in the development of these studies. There was a disparity during the past 4 years regarding emissions of 26 gigahertz that were, let's say, quite large compared to what would produce interference in our satellite systems. And there was a pushback in the radio communities that are interested in developing these regulations regarding that rather high threshold that was proposed by our government, the US government. And my understanding is that the more restrictive threshold is being considered at this point by ITU. I'm not 100% up to speed on those negotiations, but I do want to point out that the dialogue between global radio communities in the various ITU member countries is also quite important to establishing the proper regulations, the proper emission thresholds that can be accommodated to ensure that the Earth satellite services will be able to continue doing their jobs.
It's an interesting discussion on the chat about being able to measure harmful interference. Is it completely feasible to do that? That seems to be one of the issues coming out in the discussion between a couple of people. That is it. How easy is it in a technical sense to measure what could be a harmful interference between environmental sensing and communication service?
That question has sort of three answers. If there's no interference, no problem. If there's a lot of interference, no problem. You can tell it's there and you cut out the data. And as long as you're not cutting out any more than 10%, give or take, of your data, it probably won't have an impact. It's that middle region that's insidious, when the interference is present and you cannot distinguish it from a natural signal. And that has the biggest impact on weather forecasts because you just can't immediately detect it and throw it out. And there are limitations in terms of how you can go about, with reasonable computer power, detecting whether a signal that you've observed in your system has interference in it. This is an ongoing challenge right now. We've developed over the past roughly 25 years several methods of doing so. We look at, for example, the so-called fourth statistical moment of the signal, something that the mathematicians called kurtosis. And that's one way of separating what we call an anthropogenic signal from a natural signal. We also look at polarization. And there are a number of other ways of looking into the signal as well. But none of them is completely satisfactory, because there's always that possibility that that signal is small enough that it's going to masquerade. The algorithms are not going to get it. And this becomes more and more of a problem when these signals are from a large number of transmitters, because you'd think, no problem. Why don't you just look for sinusoidal signals? That's what a transmitter puts out. It puts out sine waves. Well, fine. But when you have thousands and thousands of very weak sinusoids all coming from a number of 5G or other sources, anthropogenic sources, they begin to look like thermal noise. In fact, there's a mathematical theorem, the central limit theorem, that it ensures that the distribution of thousands and thousands of small sinusoidal interferers will ultimately look just like the thermal noise that we try to measure to do our weather forecasting. So only go so far. And it's this insidious middle region where the interference is small but not so obvious that becomes the hardest one.
That's interesting. Yeah, have any thoughts on that, Tom?
No, not really. I hadn't heard of the fourth moment trick, but it sounds like it's made to order. Limitations, of course.
It's an interesting question from Scott Fox, which was talking about the 3GPP process to develop new technologies, mobile technologies, and he says they're often gated and or pulled by virtue of who owns existing or new intellectual property rights. And the process become increasingly complicated by the diversity of global voices and participants with dramatically diverse needs and desires. And he asks, how do we begin to overcome or even reduce these existing powerful forces, which clearly affects the pace of change? So to sort of put another spin on what he's saying there, do you think that the process of harmonizing and standardizing spectrum and standardizing new technologies, is there something about it which makes accommodating environmental sensing more difficult? Is it becomes such a complicated process that it mitigates against taking other considerations on board?
I guess I'm trying to encapsulate that question, but is the basic question that the entire system, political and technological, has become so complex that it makes it difficult, maybe impossible, to develop meaningful regulations and sharing mechanisms. Is that the essence of the question?
I think so, yeah. And there's also alluding to the intellectual property issues behind it, and there's often of geopolitics of different countries wanting to build up their particular standards. I assume that's what.
Yes. So there's definitely geopolitics and intellectual property add another layer of challenge to this equation. But is it too complex of a problem, in other words, to manage? Sometimes I wonder if humans are coming up against problems, real problems, that are too complex for them to manage. But I always look at complexity as inviting methods of simplification that we can begin to agree upon. And, those simplification mechanisms are, regulation is one of them. There's no doubt about that, in spite of how difficult it is, especially globally, even nationally, and how much people might not want it because it's an infringement in some sense. That still remains one overarching method. And another is scientific agreement on just what is required in order that these various services coexist. And that requires people being able to sit down and in black and white hammer out through the equations, through the data, etc., just what levels can be tolerated. So yes, it's a complex problem made all the more so by geopolitics, by IP. But I think that those two fundamental, let's say, human capabilities exist. Regulation to within reason and agreement through science.
Scott asks his question differently. He says, how can scientific use gain a louder and more powerful voice at the standards table?
Well, I first of all think continuing to be correct. When science becomes incorrect, when it becomes, let's say, too much hypothesis, too much proposal, and not enough absolute fact and evidence, it diminishes its impact. Scientists have to maintain a neutrality. They have to maintain a level of factual integrity. And they also have to continue speaking. They can't just maintain that integrity and be quiet about it. So part of that is education. Part of that is the hard stuff, the math, the science, the physics, the electromagnetics even. And part of it certainly is public support for exactly that enterprise, because it certainly doesn't exist in a vacuum without public support.
Tom, do you think there's a need for scientific use to have a more powerful voice in the 3GPP process?
Well, I think Al put it very eloquently. It's a complicated process. You're talking about huge amounts of money, huge industries. It's, yeah, I don't think I have anything really enlightening more to say on that subject.
Well, I'd like to read out a question from an old friend. He's Bo Backus, who I haven't seen for ages. Hello, Bo. I hope you're well. He asks, hi there. He asks, are we in need of a global spectrum policy to account for the need of advanced technology capabilities without inadvertently damaging critical spectrum infrastructure? Are we in need of a new global spectrum policy? Or do we only need to?
That's a really good question. And I guess my first response is sure, but where would you begin? And I think, bolstering what we now have going may be the best bet. Our ITU, for example, has been in business over 100 years for doing exactly this. And so I think supporting it maybe is the best way to move in that direction. Are we in need of it, though? We are seeing advances in the ability to radiate throughout the microwave spectrum up into the terahertz range occurring pretty rapidly, whereby now, I can go to various places on the web and buy components for, $10 to interfere with critical systems. I hate to say that, but yes, that's just about the cost of it right now. And so do we need a better and more global policy to address those kinds of new threats, that kind of proliferation of equipment? I think we really do have to at least keep up. I'm not going to say that a sweeping new policy maybe is needed, but we really do have to keep up with the rapid changes.
That is a very good point, isn't it? That the ability to buy things from all over the world, through eBay and similar, has really escalated in the past 10 years or so. And I've always, we've always been aware at Policy Tracker that that's a problem. I think we found only one or two isolated examples of it, and not as many examples of it causing problems as we expected. Is that because we're not looking closely enough, or because it's a hard thing to prove? There are lots of bitty kind of things happening in lots of different places. What do you think?
With regard to the question of a few minutes ago, I think one of the obstacles to any sort of big international agreement is, of course, the fact that the West has largely banned Chinese-made base station equipment. not allowed at all in the United States, varying degrees in Europe. And there's also a widespread perception within the United States that the United States has fallen dangerously behind in basic communications infrastructure. You want to buy 5G base station equipment, you're an AT&T or a Verizon, you have to get it either from Ericsson or from Nokia, which of course they're friendly countries, but still it's there are perceived difficulties even with that route.
An interesting question from Petri, which is the ITU tends to still think mostly from a telecommunications point of view. What would happen if IPCC would start to lobby for spectrum protection? Would that be feasible? That was a question for Al.
What would happen if who would start to lobby again? I'm sorry.
IPCC.
Yeah, I'm not sure if I. Lobbying really is an issue of who you're lobbying to, who is doing the lobbying, what their financial resources are, what their levers are. I think that we have an existing framework in this international treaty. The question is will the member countries all continue to abide by it? Will it evolve with technology needs? And will the member countries enforce within their own jurisdictions the regulations set by this international treaty? The ITU basically supervises and develops an international treaty. And so I'm not sure if lobbying, and the question would be to who, would have a big impact on that process. I could see it having a deleterious impact on that process.
And a question from Martin Weiss, or a point. Part of the challenge with spectrum policy for science is that though the economic consequences of our ability to forecast weather accurately are huge, the spectrum needed for this is an intermediate product, not an end product. Thus, it's difficult to compete against commercial users whose economic value comes from the primary product. And that one step of indirection makes a huge difference when it comes to the weight of the voice in policymaking or lobbying.
Well, there's no doubt that from a standpoint of lobbying opportunities and words exchanged, bits exchanged, scientists are outnumbered about 1,000 to 1 for lots of reasons. Financial resources, their own reluctance to speak in any other than purely factual terms, which of course potentially compromises their integrity as well. So yes, and the question of lobbying then when the odds are stacked so much against the scientists is quite a significant one. One can only hope that the truth will prevail in these discussions. I'm not sure if I have a good response to that. If we trained so many more scientists to go and speak to their representatives, I think that would help to a certain extent, beyond which the rather tricky arguments that have to be made and would sometimes require a lot of mathematical understanding and data analysis and all. It's hard for a large cadre of people to be able to make those arguments because it just requires so much training and care and study and what have you. Education certainly is at the root of it. There's no question about it, though.
Tom, do you feel, being more on the 5G and 6G side, do you feel that scientific voices are not listened to as much as they should be, or are not as influential as they should be?
I think that's probably true. However, were they ever listened to such a great extent? I mean, it happened occasionally. During World War II, Vannevar Bush was effectively the science advisor to President Roosevelt. And for one reason or another, he was enormously influential and effective.
Hmm.
In fact, after World War II, he was the one who first proposed NSF.
Is it a matter of, can anything be done about it? Is it a matter of a sort of economics, in that there's an awful lot more money in the mobile industry, and therefore, the lobbying that goes with that, and governments understandably wanting to think, what can we do to boost our economies? The mobile sector has done a lot to boost economies all over the world. And does that create a sort of an unstoppable force, do you think, that it always means they will be the loudest voices at the table?
Well, if you look at this whole problem of spectrum scarcity and the needs to reconcile all of the parties that want to use it, the very best way to get ourselves out of this difficulty is a purely technological and research one. If we researchers can somehow come up with remarkable new ways of using existing spectrum, genuine breakthroughs, that of course would go a long way towards changing things. But that says we can't just do incremental research. That incremental research is not going to, and so it really requires much more bold research. So you could rephrase your question. How do you, what can be done to encourage more bold research on the part of engineers and scientists?
Yes.
Here's an example of how demands on spectrum, I think, are radically smaller today than they would have been otherwise if a certain technology had not been developed. And I'll call it two technologies. But one is the laser and the other is the fiber optic waveguide, which carries most of our intercontinental traffic and a great deal of our national traffic as well. Imagine if those two technologies hadn't popped up, what the demand would be for the airways at this point. So, I agree with Tom that there are technologies that we just got to keep working on, even if they don't look what you'd call promising at the moment. And, when the first fiber optic waveguide was built, the attenuation was such that they could barely communicate across the laboratory. Well, now, of course, that's changed. We even have amplifiers on these systems. But it's this continual investment in the technology that can offset the demand on the spectrum that's pretty important. It's not just better use of the spectrum, in other words, it's investments in technologies that can perhaps remove that demand entirely.
Martin Weiss makes an interesting point in the chat. He says that we should build risk models of scientific use, and then that would help people to give a value to scientific spectrum. And he gives an example of how much risk reduction do you buy with an extra megahertz of spectrum. Do you think that one of the problems here is that people don't perceive a value for scientific spectrum in a monetary sense, and if that you could have some sort of conception of that monetary value, that might help? Sorry, did you think that that's a possibility, that that's a rather sort of spectrum liberalizer kind of point of view, that if people have a monetary value for something, it's more likely to be more likely to have a bigger part in policy discussions?
Martin, my audio cut out there for a moment. I missed most of that question. Sorry.
It was a question from Martin Weiss, which to my mind goes to this idea of having a monetary value for something. If you could have a better idea of the monetary value of scientific spectrum, would that help?
Yeah, so here is the big problem with that. What would be the monetary value of Central Park in New York City? What would be the monetary value of Yosemite National Park? These pristine environments that we preserved for everyone's benefit. It's really hard to put a dollar figure on that, especially because even now, if we could, how will our grandchildren want to use those resources? Will they look back and say, gee, guys, you sold off Yosemite? Come on. I don't think they'd think much of it. And then I don't think they think much of us if we did that. So I really find it very difficult, even when we have, for example, insurance needs, people's lives at stake, which somehow can be costed at something like several $1 million a life, if you want to put it in actuarial terms. I find it very difficult to apply those arguments to the value of the somewhat small and capped portion of the spectrum that's needed for passive services.
We're coming to the end of our allotted time, and what you were saying there reminds me of a story that always amused me, which was that some friends of mine bid to do some work for the European Defence Agency, which was to value defence spectrum. And their central argument was that if defence spectrum, we didn't have this defence spectrum, then Europe could be invaded by some pernicious government, and then the economies of Europe would totally collapse and would be utterly worthless. So it's impossible, therefore, to put a value on defence spectrum. It has an infinite value because it guarantees national security. And unsurprisingly, they didn't get the contract. So it's the same issue that you raised.
You know, there is one number that I have seen floated around: the cost of mitigating climate change, which some people float around at about $50 trillion. That cost might not have to be borne if there was enough evidence that the mitigation would be necessary. And that evidence is, to a great extent, through our scientific understanding of the globe, through our sensing techniques. Sure. So, you know, it's a very indirect connect the dots, but nonetheless, it's a large number.
Yeah, no, quite. Yeah. And I suppose that was the point about the defence spectrum. They sort of, you could argue an infinite number in a way. Tom, if I could move back to you, would you like to make some concluding remarks as we've come about to the end of our time? Then I'll come back to you, Al, if you can make some concluding remarks as well.
Well, in general, I'm actually optimistic long-term that this general problem we're talking about can be solved. And again, I think as engineers and scientists, we just have to strive to be far more innovative than we are now. In general, what we see is industry isn't doing a great deal of fundamental research anymore. I don't know where they expect the research to come from that will keep them going long term. There are exceptions here and there. Some of the West Coast companies are investing in quantum computing and related things. Bell Labs still exists and does some fundamental research in various areas. But at the universities, it's, you know, it's too easy as an academic to fall into the trap of just doing what you're comfortable doing. Ready sources of funding for a stable of students. The students turn out their requisite 3 refereed publications, get their PhD, and the cycle continues. It's so again, one question is, how can we persuade all of these talented people to take some more risk in what they're doing?
Well, thank you. No, thank you. Al, what's your concluding thought?
My concluding thought probably might sound a bit boring, and that is, I think we have many of the mechanisms in place to begin to solve these problems: regulatory mechanisms, international treaties, scientific understanding, technology development. And it's going to be continuing all those areas that I believe are going to be relevant to our resolving these problems, along with one more that Tom mentioned as well, and that it has to do with leadership of students coming up now and writing their proverbial 3 papers. This is a particularly developing area. And I would say 30 years ago, if I was to advise a student whether they ought to go into spectrum management or not, I'd say, well, you know, it's not going to get you rich. Well, maybe today it won't get you rich, but it'll do you pretty well. And it's becoming more and more important. And there's an off-ramp into this area called electromagnetic compatibility that actually could get you quite rich these days. So I think that in development of our student leaders, we have to recognize that our use of Maxwell's equations has changed a little bit. And we're not all just trying to figure out how to send signal from antenna A to antenna B. We're trying to figure out how not to send signals from antenna A to antenna B. And that's equally important.
Thank you very much, Al. Well, I'll hand back to Martin Weiss, and hopefully, Martin, you'll take the opportunity to explain your comments a bit more thoroughly than I did. I feel I didn't do it justice, so I'll come back to you.
Oh, well, thank you. No, I mean, this is an idea that has been rattling around in my head. And so, Nick pointed out that we talk about the marginal cost and marginal value of adding spectrum. Now, suppose you could buy a certain amount of risk reduction by adding, let's say a megahertz to earth sensing, let's say for a margin. Some of these things are computable. You brought out the value of Central Park, and there are people who try to value these things. And some of the proxy values that they use are things like, let's look at the real estate that's right next to Central Park, and that turns out to be extraordinarily valuable. So there are proxies that are available, and they're useful proxies. And I guess just because it's difficult doesn't mean it can't be done. And even if we don't do it exactly directly, we can come up with proxies. But this notion of trying to value something that's an intermediate product for something else, again, this is some economists can do these kinds of things, but I think the more we can capture the social value of scientific spectrum in language that resonates with people who normally attend the ITU events and so forth, I think the better off we are. And this notion of risk management and option value for spectrum, and these are all different ways in which these are languages that some of the people understand a little bit better. So I guess that's the essence of my little speech about that. And we can have conversations offline about that more anyway. So I guess I guess we're, as Martin has pointed out, we've kind of reached the end of our time. We're welcome. I mean, if people want to stick around and chat, I think the room will stay open for a while. I know other people have other places to go. For Martin, it's getting rather late, I suppose. It's maybe supper time. So, and I know we all have other things to do. So I suppose we'll drop off. But if anybody, I suppose, wants to stay, we can maybe hang out for a little bit longer.
I'm going to go, as you rightly said. It's